MSMT and how we can design the system using LG's membrane software. This video is that we will not go in details for the MSMT as a design, because we have a separate video explaining everything about the MSMT multi-stage multi-turbo configuration. But we go very fast through the idea, and after that the main focus it will be for LG to design LG using LG membrane software. The idea of MSMT to have maximum recovery in seawater or low seawater. The best TDS we can use MSMT on it, it's from 30,000 ppm up to 40,000 ppm. The reason for that, the limitation of the membrane pressure, which is 84 bar or 1200 psi. For that we need to be in this range to use standard pressure vessel, standard membrane, standard everything. Over than that, we can use MSMT, but with the new ultra high pressure vessel and membranes, and this will be economy in the future to use it as a standard. But for today we use this ultra high pressure vessel and ultra membranes for project like zero liquid discharge. But we will cover now only from 30,000 to 40,000, which can be increased the recovery from 65% till 55% in 40,000. For that, it's huge increase in the recovery. If we see normally we in 40,000 ppm, we only go through like 45% recovery. To increase this recovery by 10% to get a lot of benefit. Like you decrease the amount of pre-treatment, you can increase the size of the plant with same flow, especially if you use like containerized system or something like that. For that, with same footprint, you can get more product water. And again, this is new technology or new setup. You can use it in the sites like you have very limitation in the feed resource, like in some area you have limitation in wells and the feed water is not enough, or in the container, and you need to maximize feed flow from these containers. Let's start. As we know, the main challenge we have it in multi-stage system is the possibility of scaling and fouling in second stage. Mostly this has happened because we, in normal design, we work in very low flux in second stage or third stage in all the things. For that, because this low flux, we have this problem for scaling and fouling. For that, I know many of the designers is not big fan to have many stage system, but with MSMT we make flux balance between the stages. For that, we allow to have the most flux effective based on the manufacturer recommendation between the first stage and second stage, so that we have almost same flux between the two stages. For that, the second stage is working exactly in the standard flux based on the membrane manufacturing standards. For that is minimize the possibility for flux and fouling. As we can see here, the setup is high pressure pump, turbocharger, feeding first stage, then the rejected from first stage goes through the turbocharger to post pressure to second stage, and the rejected from second stage go to power the first turbocharger. And here's the idea, because the turbocharger here is most efficient, it's very high efficient. For that, the amount we needed to post, it's less than what we can generate it from this turbocharger. For that, we send the extra amount to the first turbocharger or the feed turbocharger, and we recover this amount, and after that we pump it out the reject. For that, we have here in this system two turbocharger, and the good things, this two turbocharger is designed to be fine-tuned together. For that, we designed the interstage turbocharger to post pressure as according to the membrane projections, and after that it's already sent without any valve, without anything between the two turbos. They are communicate each other and work together very fine to use or maximize recovery from the reject, the power from the reject. Now we start in LG membrane projections software. Here we put project information that we're going today to design 2000 cubic meter per day plant case in 60,000 ppm. Okay, we put the project information, and after that we go for design. In LG you have library for the TDS. It's like it's 2,000 different steps. If you have your own or the actual analysis for the feed water, you can add it, but now we will use one from the library, which is 66,000 ppm feed water resource. That we go with seawater open intakes as a worst case scenario. Here, this is the water profile as we use it from the library. If you have actual water TDS, then you can add new and you start to put your water analysis here, but we will go with the what we have. Temperature, we go also, when we design, we start with the worst case scenario. For that, I will go for the lowest temperature we can have. pH 7.5, and again, worst case scenario, I will make it in year 3, can make it in year 5, but normally we make it with year 3. Then now we start to go for the design. We go with the feed and recovery. Feed will be 160 cubic meter, and we start with recover 65% and see if we can reach this recovery. Now we start and design the system. For guidelines, I like to keep the flux between 12 and 13 or 12 and 14 maximum. For that, normally I use the product water divided by 12.5 to get idea about how many membrane I will use. For MSMT, again, it's for myself, if we go through all the old books, when you go for the seawater, it's recommended to go to a shorter pressure vessel. Actually, because this is the last 2 element in 6 element, or the last 3 element in 7 element, the productivity you get it from this element is so low. because it's working for very high TDS. For that, in MSMT, we commit to working with 4 pressure vessel lengths. This will be give you more results. And again, the idea here, because we're working in limit pressure for second stage, for that each bar we saved from first stage allow us to increase the recovery in second stage, so that we go with 4 element pressure vessel. Second point, because the first stage is working with less TDS, for that I am able to use low energy membranes in this stage to save power, and at the same time, because they're working in low TDS, so that I guarantee I get good water quality. For second stage, because we go with high TDS, we recommend to go with the high rejections membrane to get most low TDS for the production. The idea when we mix post production, we be under 150 to be good to go without second pass. For that, this is the guidelines again to make the design more easy for you guys. But if we goes with that, we have 2,000 cubic meter per day plant divided by 12.5. Then we need around 160 element. If we divided this by 4 to see how many pressure vessel we need, we see like we need around 40 pressure vessel. Again, according to standard, you need to go almost around 2 to 1 for pressure vessel between the first and second stage. So this 40 divided by 3 and times by 1, so that we supposed to go with 26 pressure vessel for the first stage and 4 element. And again, we go with the LG SW440 SR for the first stage. Then we add second stage. We use a 14 pressure vessel. And 4 element, and we go with GE 440 GR for this stage. The idea here, we need to add pressure between the 2 stages so that we use the tool of post pressure. And I will start with 22 bar post pressure between the 2 stages and see what we get as a result. Calculate. Here, this look like we have wrong or alarm for the first stage. We go for detailed design to see what we have. Here flux is 11.93, which is low, for that I can save some element of membrane element. I can reduce it because I still have good room. We see here the pressure is 81.85 in the worst case scenario, that it's acceptable. We go for flux. The flux for the first stage is 12.05. The second stage 11.67. We are very close, which is look like good result till now. Then we go to see what alarm we have to try to avoid this alarm. This is a table for each element, and here we have only one alarm, which is we exceed the minimum value of reject water with 3.2 cubic meter per each element, and we can see where we have that. It's clear, it's here, because here we have only 3.1 sorry, 3.03. Okay, this is the only one we have here. Let's look, everything is good. Okay, for the first trial, it looks like we are good. Then what I will do, I will increase the post pressure here to 23, and I will drop the pressure vessel here to 25, and see as the result. Calculate. Oh, okay, it looks like we have a good design, no alarms. We go for design. Okay, now flux, average flux is 12.123, which is good. We go here to check the flux, 12.22, 12.23, excellent. It's totally balanced between the two stage. We go down, no alarms. Here 3.2 something here for reject. Okay, permeate water, like everything look good. We see the pressure 82.6 for worst case scenario. That look like we have a good design here. For that we success to achieve 60% recovery in worst case scenario. Okay, we use 156 membrane. Flux is good. We have totally flux balance between the two stage. For that we are good. TDS 74 for first stage, 145 for second stage. Look perfect. For that we see the total permeate TDS it will be 99 under 100. That's look good. That's look like everything's looking good. Now we can print this one, and now we have the first design for worst case scenario. Okay, now we can check same things in year 0 and temperature 35. Okay, year 0, temperature 35, to see if we have any problem. So looks like we have alarm. In this case, we go to see what's the problem we have. And alarm is with reject. Okay, the problem also is the fourth element in first stage. Okay, we see the flux here, what we have. Okay, then we back and see if we increase this to 24. Alarm is gone. See the details. Okay, almost we have flux balance, and here no alarms. Everything's looking good. Okay, then we can keep the same recovery for the post cases, the worst case and the lowest case, and now we are 100%, we are sure all the other points will be good for us, so that we can go back and start working for the other point we need, like 25 in year 0, 25 in year 3, and all these other cases, because now we guarantee the highest and lowest point it's working in this design. So that now we achieve 60% recovery in 36,000 ppm, which is decrease the feed flow decrease the pretreatment system, decrease the chemical I will use in operation, because the chemical is dosing in feed flow, so that when I decrease the feed flow, automatically the chemicals will be reduced, chemical consumption will be reduced. I hope I success to explain to you how to use algae membrane to design two-stage design system with turbocharger. Just when you send us this membrane projection, we are able to select the correct turbocharger for interstage turbo and feed turbo with high pressure pump, give you the total system designed very easy. Thank you and goodbye.